Welcome to the session on embedded systems. Today we are going to see the hardware architecture of embedded systems. As we know that embedded systems is a combination of hardware and software, we need to know about the every building blocks of the hardware architecture and the functional importance of each and every block. So when we come to the hardware architecture of an embedded systems, we have the CPU, we have sensors, we have LEDs, LCDs, communication interface, memories, chip select, debugging units, and so on. Among the hardware components, the CPU is called the heart of the architecture. When it comes to the CPU can be a microprocessor in case if the embedded system has a large software and which has to be loaded onto an external memory, we go for a microprocessor. If the embedded system has a small software that has to be loaded on the small internal memory, as we know that the footprint of the internal memory is very small, we go for microcontrollers. And along with the microcontroller, we can make use of the inbuilt function units such as the ADC, DACs, CAN nodes, all the inbuilt circuits as per the requirement. So the microprocessors and microcontrollers, it is not necessary that there could be only one processor or one microcontroller. So many more than one processors and microcontrollers can be as a heart or the CPU, but one will be the main, other works as the coprocessor mode. So before going in detail about all the building blocks in the hardware architecture, let us discuss about the heart of the CPU. The heart of the hardware architecture is called the CPU. The CPU consists of a general purpose registers, ALU, stack pointer, memory address register, instruction pointer, and memory data register. The ALU, the main operation of the CPU, is the arithmetic and logical operations. In order to perform the arithmetic and logical operations, the CPU makes use of the general purpose registers. The general purpose register holds the data for the operation and also stores the results. And coming to the next block, which is nothing but the control unit. The control unit consists of the instruction pointer, wherein the instruction pointer has the current instruction that is to be executed. The instruction which is being on the instruction pointer is decoded by the instruction decoder. Once the instruction is being decoded, it is ready for execution. At the moment, if any interrupt arises, the instruction in the instruction pointer has to be loaded onto the stack, and so that the processor attends the ISR, which is nothing but the interrupt service routine. Once the interrupt service routine is being completed, it comes back to the stack, fetches the instruction and resumes its operation. So from the next block is called the memory address register, which holds the address, and the memory data register, which holds the data required for the operation. So when we deal about the buses that has been connected to the CPU, or three, nothing but the address bus, data bus, and the control bus. The address bus is unidirectional since it is going to fetch the information only from the memory. The data bus is bidirectional. Since it is going to fetch their addresses from the memory, and as after the result of the arithmetic operation, it is going to store the result back to the memory. So it is going to do to and fro operation, hence it is bidirectional. The control and status bus have the status signals such as read, write, memory write. Is it an IO read? All the operations are indicated by the status bus. So now we discuss about the address bus, data bus, and the control bus. So as we know that the address bus is unidirectional, the data bus is bidirectional, as well as the control bus. So based on the program and data bus, the processor architecture are being categorized into three. One is called the von Neumann architecture, and the second one is called the Harvard architecture, and the third one is called Super Harvard architecture. When we come to the von Neumann architecture, the von Neumann architecture, the CPU has a single memory chip which holds the instruction as well as the data. So the instruction and the data are being handled by the address bus and a data bus. So whenever the CPU has to fetch some instructions or data, it has to use these dedicated buses. This von Neumann architecture, it is very simple. As it is very simple, it is widely used. So the next architecture is called Harvard architecture. When we see about the Harvard architecture, the CPU has a separate program memory and a separate data memory. The data memory holds the data and the program memory holds the instructions. As we see in this picture, the data memory has a unique data bus and a address bus. Similarly, the program memory has a unique address bus as well as data bus. So, when we compare this with the von Neumann architecture, the CPU processes the instructions and the data at the same time using the dedicated buses. So, because of this facilitation, this Harvard architecture is faster and efficient. The third architecture is called Super Harvard architecture. In the Super Harvard architecture, the CPU has a separate data memory and a separate program memory. So, what is the difference between the Harvard and the Super Harvard? So, some part of the data memory which is being frequently used is being stored as a secondary data in the program memory to balance the load between the data memory and the program memory. As the Harvard architecture, this Super Harvard architecture has a dedicated address and data bus for program as well as dedicated and address and data bus for the data memory. So, this type of buses are mostly used in the DSP processors. So, as we categorize the processors based on the program and the data buses, we also categorize the processors based on the instructions. So, categorization of processors based on the instructions are being done like CISC and RISC processors. CISC is called complex instruction set computer and RISC is called reduced instruction set computer. Then what is the difference between CISC and RISC? CISC processors have large number of instructions, when RISC processors have few number of instructions. And CISC processors have a variable length instructions. Here the instructions are fixed length and the complexity here is little bit more in CISC, wherein here the processor architecture is very simple. So, there are some differences between the CISC and RISC. So, let us see what are the differences that categorizes the process into CISC and RISC. So, based on the instructions, we categorize the process into CISC and RISC. CISC processors have large number of instructions. As the name implies, RISC processors have reduced number of instructions. CISC processors have limited number of registers. So, normally it varies from 8 to 16. RISC processors have more number of registers. Normally it can go up to 256 also. The instruction length is variable. The instruction length is fixed. This requires lot of clock cycles. This requires a single clock cycle for instructions. Reduce software complexity but increases complexity in processor architecture. Increases software complexity but reduces complexity in processor architecture. So the examples of Cisco processors are 8086, Motorola families. Here examples of RISC processor are your ARM, Atmel, AVR, PIC, etc. So today we have discussed about the hardware architecture, in which the processor architecture has been discussed, which consists of von Neumann, Harvard and Super Harvard architecture. And we'll discuss about the memories and clock circuits, timers, etc. So when we come to the input and output devices, we have to speak about the DMAs. So when we come across the DMA, so the DMA is called direct memory access, which is used when the memory has to directly communicate with IOs. Hence, when the direct memory access comes into picture, we have the CPU, we have the memory, we have here the DMA controller and the IO device. So the CPU will be the master and all the devices will be as working as slaves. Whenever the IO device wants to communicate with the processor, every time it has to have a request, and then the request has to be granted by the processor. If the IO device has a huge amount of data that has to be stored to the memory, so it goes for the direct memory access. Once it takes over the control of the three buses, address bus, data bus and the control bus, the IO device can directly access the memory without the intervention of the processor. So after the communication has been over, the IO device hands over the control of the buses to the processor. So this is called DMA memory access. So today we have discussed the hardware architecture. So in the hardware architecture, we have seen the CPU. When we come to the CPU, we have seen the CPU in various modes of architectures, von Neumann, Harvard and RISC instructions, etc. So when we come to the memory, so we have two types of memory. One is called ROM, which is non-volatile, and RAM is volatile. So the informations that has to be permanently stored in the ROM is being loaded on your ROM device. So ROM, which is nothing but the permanently burnt program, can be written on the ROM, and there are several types of ROM, which is nothing but is called PROM, EEPROM, which is erasable, programmable, read-only memory, and other one is called EEPROM, electrically erasable, programmably read-only memory, and then this one is called flash memory. So in the flash memory, it is also electrically erasable, programmable, read-only memory, but the difference between the EEPROM and the flash memory is that it has been electrically erased to that is the segment level. The entire block has been erased in the flash memory, wherein the EEPROM only the registers have been erased. So that the permanent data is being stored on the ROM, wherein the RAM memory is volatile. It holds the stack, input and output, buffer data, so all the data handlings are being handled by the RAM. So the permanent data have been handled by your ROM. So the debugging port is used for debug operation. Next is the watchdog timer. The watchdog timer is an electronic timer which has a higher counter value and keeps it decremented in the normal operation. So once it is been decremented, again it starts to initiate to a higher value and keeps on decrementing in the normal operation. When the watchdog timer fails to reset itself, if there any hardware conflict occurs, then it gives a timeout signal. This timeout signal is used for the correction operation. So when schema intervention is not possible to reset a system, and when the watchdog timer fails to reset itself by an ordinary method, then a timeout signal is being given. So watchdog timer keeps on watching every operation of the processor. The chip select unit. The processor or the controller works with a number of peripherals. So if we want to know about the current process, it is been identified by the chip select unit. The clock circuitry. The clock circuitry is used for synchronization of other devices within the processor. And the clock signal is being generated with the help of the crystal oscillator. The higher the clock frequency, the higher the speed of the system. Power supply unit. Power supply unit is necessary for the power supply, which ranges from plus to minus 3.3 volts to plus or minus 12 volts. So the DAC is used as a digital to analog converter, wherein the ADC is responsible for analog to digital conversion. The sensors will act as an input unit which gives input from the outside world. So if the sensor value has to be converted to digital before processing, then the analog to digital unit converts this analog data to digital data. The LEDs and the LCDs are the output devices. The functional keypad is used for any specific operation that depends on the task. So the last one is the communication interface. The embedded system communicates with the outside world through the communication interface. There are several communication interfaces such as RS-232, RS-422, Ethernet, Bluetooth, Wi-Fi, etc. So hence in this session we have seen the hardware architecture of the embedded system. We discussed about the CPU. We discussed about each and every block in this architecture. So this is about the building blocks of the hardware in embedded systems.